Welcome to Engaging Ideas, where we bring information and ideas from the Academy to the community to help think about real-world questions. Computing devices, servers, desktops, laptops, tablets, and cell phones dominate our lives. Consider just cell phones. In 2017, the number of cell phone subscriptions passed 5 billion, meaning that nearly 70% of the entire world population had a handheld computing device that we call a cell phone. Add to this several billion personal computers, an uncounted number of corporate servers. For example, Amazon's cloud alone uses 1.3 million servers. And the total number is simply staggering. Our topic today is about the computing revolution, specifically about the ways in which information, technology, and energy are related to the world of computing, and just what that means for our future. Joining me is Dr. Barry Zink, professor in the Department of Physics and Astronomy at the University of Denver. Professor Zink's research is in experimental condensed matter physics, exploring heat, charge and spin flow, and nanosystems. His research has applications that range from nanoscience to non-proliferation. Professor Zink is the author or co-author of nearly 50 scientific articles for professional journals. His research has received support from numerous organizations, including the National Nuclear Security Agency and the National Science Foundation. Professor Barry Zink, welcome to Engaging Ideas.
Thank you, Jim. It's a pleasure to be here.
Barry, you've said that information, which we usually think of as intangible intellectual quantity, is actually grounded in the physical world. Could you talk more about that?
Sure. Maybe the most helpful way to frame this discussion is to think about messages.
Okay.
So 10,000 years ago, let's say you wanted to send a message to another person. You basically, if they're not sitting there in the room with you, you'd have to tell somebody, and that person would then have to carry that message.
Mm-hmm.
That doesn't seem all that physical, although there's a physical person that's carrying the message.
Right.
But then once writing is invented, you can write something down. And once you've written something down, it's pretty obvious that that's a physical manifestation of information. Mm-hmm. Then the printing press is invented, and now we can make lots of copies of the same information, and then we can fill libraries with information. So those books are a physical manifestation of information. Now, instead of books, we have things like this, right? So the vast majority of the information that we use and process and interact with every day is actually stored on a thing like this. This is the inside of a magnetic hard drive. And the information is stored in this magnetic material that is this shiny thing there. And it's stored in the form of tiny, tiny bits, that's ones or zeros, and all processed digitally. And this is now what we think of as the physical manifestation of information. But of course, I have to remind you that if you go back even 10,000 years ago, this information that was stored in a person's brain, that is also a physical manifestation, right? Because your brain is this massively connected network of neurons, and those neurons are all talking to each other on the molecular level, and that is a physical manifestation of information. And so really all information is a physical thing.
Let's talk a little more about that in terms of the relationship between information and technology. Can you explore that a little further?
Well, sure. I mean, somehow we got from just walking next door to talk to your buddy to this thing, right? And how did that happen? Well, we went through writing and the printing press, but things for information really got kicked off when we started talking about the information age, only after we first developed these things, which you may remember. These are vacuum tubes, right?
Right.
And what they are is the technology is simply about like a light bulb, right? But it's a way to control the flow of electrons. And so it's a switch. And it's this switching, this ability to turn from a 1 to a 0, that allows information to be stored and processed in this digital way that then ends up in the hard drive. Along the way, of course, we've got to figure out how to go from switches that are this big to switches that will allow this technology where they're billions and billions of times smaller. And that's been the massive success of a huge amount of effort in research and engineering in nanotechnology. And that's what's really fueled the information age. So now our switches are not these things anymore, but they're these billions of tiny switches that exist in the CPUs and other parts of our cell phones and our computers. And that's how we store, move, process information, is by moving electrons around into and out of these tiny switches.
And so we've moved from the vacuum tube to the integrated circuit to now these very complex silicon-based
That's right, and I have
technologies.
a silicon wafer here. This is a really small one compared to what people use now. But the essential development really was to stop moving the electrons around inside a vacuum. That's what the vacuum tube is. There's no air in there, right? And start moving them around inside of a material. And that's what this material is, what this silicon is we now move the electrons inside tiny circuits in the silicon material. And some examples of some rather simple integrated circuits I happen to bring. And so here's a few that I made some number of years ago with some collaborators at the National Institute of Standards and Technology. And here we've got tiny wires that all move these electrons around and enable the functionality of these particular chips. Now these are rather specialized ones that are made for measuring tiny magnetic fields. But the ones that in our cell phones and computers are much more complicated, with billions and billions of these little switches, maybe 10 billion switches inside of a central processing unit that would drive a computer or a cell phone now.
So we've talked about this evolutionary process. So what are some of the implications of this?
Well, one of the implications that people don't often think of is the amount of energy that's required by these types of
Even by these little circuits?
even with the little circuits, right? Because you knew that energy was generated or consumed in a switch like this if you ever met one when it was operating, because they'd get hot, right? You would feel the hot wind blowing out of whatever this was. And so that obviously you had to worry about how much energy that was costing. Now that we're into these tiny things, of course, you might think that the energy isn't so important. And indeed, if you look at the amount of energy that's required to just flip one of those switches, it's an incredibly tiny amount of energy. It's so tiny, it's difficult to think of. One way to say it is that one estimate of that energy is that it's about 1% of a femtowatt.
And what is that?
Yeah. Well, nobody thinks about femtowatts or femtojoules, and so 1% of a femtojoule is 10 to the minus 15 joules, and the best way I can give you to sort of maybe get a feel for how small an energy that is it's about 10 billion times smaller than the energy that a mosquito generates when it hits a wall. So it's a really small amount of energy, but we then, in the process, when we use a computer or we use a cell phone, it's doing switching at an incredibly high rate of speed, and with many, many of these switches happening all at once. So that at the end of all of that, the computer chip is generating something like 100 watts. It's consuming the amount of energy every second that a light bulb or something like this really did. And so that's about where we are now in terms of how much energy each particular CPU generates. But then if you think about what happens when you use each CPU, you can start to get to staggering amounts of energy that are consumed in the information economy.
So as I indicated in the introduction, we've seen this huge growth of computing in all kinds of devices. Seems like it's never ending. And I assume then that's translating into a huge demand for energy.
Indeed it is. If you think about the amount of energy that's required, right about now people estimate that maybe 5 to 15% of our energy production capacity is consumed by computer and information related technologies, which is already a lot. But it's also growing at a tremendous rate, as you mentioned. And it's kind of strange because you don't necessarily think why that might be, but if you give somebody, let's say you give somebody a car that's twice as efficient. Now there are going to be a few people that will just drive twice as much, but not very many people, right? People usually drive based on what they need to do every day, and it doesn't change all that much. But if you give somebody a computer that is 2 times faster or can process 2 times more information, they find new things to do with it and new capabilities, and they explore different types of things. And so by giving people more powerful computers, the demand that we put on their use continues to increase. Now that's a good thing in a lot of ways, but it does mean that if you take the amount of energy that we use on computing now and you project it into the future, some people estimate that by as soon as 2030 that we could be using our entire energy generation capacity just on information technology related things. And that's obviously a problem.
Now, as you talk, it occurs to me that when I pick up my cell phone or something and use that, it's not just probably the energy in the cell phone, but am I not triggering a bunch of events?
You make an excellent point, right? It's one of the things that's amazing about computer technology is that each single computer we interact with is able to get so much new information to us, right? We can download a movie, we can email people, we can see websites, we can do all these different things. But every time you interact with something that fires off a signal to this massively interconnected web of computers, you're turning on not just the cell phone in your hand, but you're turning on some number of, I don't know, thousands of other computers that then are generating energy. Now you may not see them, you don't know where they are even most of the time, but there's a huge interconnected energy cost that comes.
So there's the energy dimension, but I've also read that there's this sort of limitation on silicon chips in terms of their physical ability to process.
Yeah.
So we have the dilemma of the energy, we have the limitations. So where do we go from here?
Yeah, it turns out that the limitation on silicon chips is also related to energy, and specifically it comes back to heat. So people talk about Moore's law. You may have heard about that. That's this idea that if you continue to make nanotechnology better, that you can double the number of those switches on a chip every year. And that has worked for quite a long time, but people are now predicting that we're gonna, with traditional silicon nanotechnology, we're gonna run out of steam with that sometime maybe by the next few years, even as soon as 2020 or 2025. And so there are lots of people that are concerned about trying to figure out how to make better computers. Now it turns out the reason, as I said, has to do with heat, because the way we currently make these switches run is by controlling electrons, just the same way we did this way. It's just we have a much better way of controlling the electron flow now. But moving electrons around costs energy. Whenever the electrons are bouncing around, they transfer a bunch more energy than that mosquito hitting the wall eventually. And so that leads to heat, and getting rid of the heat can be a big limitation on how these chips work. So yeah, that's part of why Moore's law is going to end, and we're going to have to do something different. You have to either get rid of that heat somehow, or you have to do something totally different and disruptive and make a computer in a different way.
What kinds of options, Barry, are out there? Are there alternatives?
Oh yes, there are definitely alternatives, and there's lots of different things that people are exploring. I can tell you most, hopefully intelligently, about the one that I'm most interested in, which is called spintronics. And so that's an area that we're researching here at DU in my lab, and also with collaborators here at DU and in other institutions across the world. And it goes back to the idea that the information that is carried by an electron in current technologies and these very old technologies is all about what's called its charge. And that's a fancy physics word for saying how that electron interacts with electric fields. And it turns out there are other properties of electrons that people don't necessarily think about, but electrons also have what we call spin. And spin means that each electron, this tiny particle that's too small to even think about how big it is basically, each one is actually a tiny magnet. And like a magnet, it can be either having its north pole pointing up, or it can have its north pole pointing down. And so that is a built-in way to encode some different types of information into a stream of electrons, because you can not only have them moving around based on their charge, but also organize their spin degrees of freedom so that you can encode information in them. And so this idea of using the spin is spintronics. That's adding the spin to electronics. And one of the big exciting things about it is that there may be a way to use this spintronic technology to move information around without even really using the motion of electrons at all, to encode the information in spin degrees of freedom in materials that don't have electron flow involved. And then if you get rid of the electron flow, you can get rid of the heat, and that's a huge win for potential computing technologies.
Well, that's just remarkable. And is this a dimension of the nanotechnology that you're working in?
For sure. Now, I work on very fundamental questions, and there are lots of these big science questions that we still have to answer. But yeah, the hope is very much that the questions that we can answer in the lab here on the campus at DU can eventually lead to revolutions in nanotechnology and enable continued growth in these types of technologies and really helping solve a societal grand challenge of how to make computers better and how to use energy responsibly.
What an interesting and important topic. Dr. Barry Zink, thanks so much for talking to us about this engaging idea of the relationship between information and energy, where we stand today and where we may be going in the future. I hope you'll join us in the future as we bring more engaging ideas from the Academy to the community. I'm Jim Grismer. Thank you for watching.